In this lecture, we are going to discuss composition of linear transformations and multiplication of matrices. We introduce matrix product as a matrix manifestation of the composition of linear transformations. Let's begin with a general discussion of a composition of function. So, definition. So, given functions f from the set A to the set B and g from the set B to the set C, their composition is a function h from the set A to the set C given by, so h of x is equal to g of f of x for x an element in the set A. Now, if we take an element x in the set A, when we apply f, we obtain an element of the set B, and now we can apply to the result the function g, and that will produce the result in the set C. So this will be the composition of two functions. So the notation that we're going to use is we write that h is a composition of g with f. And so here we have a warning. So this is just a little bit counterintuitive. When we write that h is a composition of g and f, so in expression g composition with f, f is applied first. So just as in the expression g of f of x, right? So f sits on the right of g, but as a function, this function is applied first. So this one has to be aware of this convention and follow it. Let us state the following basic yet fundamental property of composition. Proposition. So suppose now we have three functions. So let f x from set A to the set B, g x from the set B to the set C, and h x from the set C to the set D. Then we have the following. So if we take a composition of f with g and then take a composition of this with h, the result is the same as if we take a composition of h with g and then take the composition of that with f. So here the order of functions is the same. So f is on the right, g is in the middle, and h is on the left. So what is different is how we group things. So for example here, so this composition will become a new function which acts from the set A to the set C, right? And then when we take composition with h, we get a function from A to D. Now here, this composition produces a function from the set B to the set D, and then composing it with f, we also obtain a function from A to D. And so the claim of these propositions is that these two compositions are the same. Now the proof of this proposition is elementary. So we just apply both left-hand side and the right-hand side to the same element. So apply both sides to an element x in the set A, and verify that the results are the same. Now, for the left-hand side, so what do we have? So here we have h composition with G composition with F apply to X. By definition of this composition, so this will be H applied to composition of G with F applied to X. And applying the definition of a composition again, but now with G composed with F, so this is H applied to G of F of X. Now if we do the same thing to the right hand side, so we will have H composed with G composed with F applied to X. So this equals H composed with G applied to F of X. And now by definition of a composition, this is H of G applied to F of X. And what we see is that the left hand side is equal to the right hand side for all elements X in the set A. So this means that these two expressions are the same. So this equality is called associative law for compositions. And this proposition tells us that in a very general context, compositions are associative. Now let us discuss compositions in the context of linear transformations. So we have the following theorem. Let T be a linear transformation from the space U to the space V, and S be a linear transformation from space V to the space W. Then their composition S composition with T is a linear transformation. And this linear transformation will act from the space U to the space W. In this theorem, we need to prove that this composition is a linear transformation. So this amounts to two things. One, that for all vectors u1 and u2 in the space U, we have S composition with T applied to u1 plus u2 is equal to S composition with T applied to u1 plus S composition with T applied to u2. And the second thing is that for all vectors u in the space U and for all scalars C in our field, the composition S composed with T applied to C times U is equal to C times the composition of S with T applied to U. Now let us prove the first claim. So here it begins with the quantifier that for all u1 and u2 in the space U. So whenever our statement starts with a universal quantifier like this one, then what we do is we write the following. So we say let u1 and u2 be arbitrary vectors in the space U. Now, if we can prove a certain claim for arbitrary vectors, then this claim will hold for all vectors in this set. Let us start with the left-hand side. So here we have S composition with T applied to U1 plus U2. First, we use the definition of a composition. So this is S applied to T of U1 plus U2. Now we use the fact that T is a linear transformation. So it's given to us that T is linear. A linear transformation will transform a sum into the sum. So this means that T of U1 plus U2 is equal to T of U1 plus T of U2. So now we use the fact that S is linear. And we use the same property of a transformation S. And what we get is S of T of U1 plus S of T of U2. But here, so this is nothing but a composition of S with T applied to U1 and the same composition applied to U2. So we get that this is S composed with T applied to U1 plus S composed with T applied to U2. And that's exactly the right-hand side that we need to obtain. So this proves the first claim, the first property of a linear transformation, and the second property of a linear transformation. As usual, I leave it to you as an exercise. Now, let us recall how we construct the matrix of a linear transformation. So let T be a linear transformation from Fn to Fm. So the matrix A of linear transformation T is an M by N matrix formed by placing images of basis vectors So we take the standard basis vectors E1, E2 up to En. So we apply the transformation T to these basis vectors. So we obtain vectors in the space Fm, and we place these vectors as columns to form a matrix. Once we have this matrix, we can calculate values of this transformation on arbitrary vectors by using matrix vector product. So then T of some any vector v is equal to the product of the matrix A with the vector v. Right? So this is a product of a matrix and the vector. Now we would like to answer the following question. Suppose we are given two transformations with their matrices. Now, how can we calculate the matrix of the composition of these two transformations? Let T be a transformation from Fn to Fm, and S be a linear transformation from Fm to Fk. So with matrices A and B, a respectively. So what is the matrix of the composition S with T? We apply our standard rule. So to form the matrix of a linear transformation, we need to apply this linear transformation to standard basis vectors and place the results as columns to form a matrix. Right? So we form a matrix by placing S composition with T applied to E1 up to S composition with T applied to En as columns. But what is S composed with T applied to E1? So by definition of a composition, this is S of T of E1. Here we use this property, that when we apply a transformation to any vector, it's the product of the matrix of this transformation with that vector. The matrix of transformation S is the matrix B. So this means that this result is B times vector T of E1. But what is the vector T of E1? So T of E1 is the first column of matrix A, because this is how we form matrix A. So we form matrix A by placing T of E1, T of E2 as columns. So this means that T of E1 is column number 1 of the matrix A. And here what we do is we take the product of a matrix B with column number 1 of matrix A. So likewise, when we compute S of T of EI, so this is going to be S of T of EI, and this is equal to the product of matrix B with column number I of matrix A. And so then we compute all these vectors and we place them as columns to form a matrix. And this matrix will be the matrix of the composition of S with T. So this leads to the definition of the product of matrices. So let T be a linear transformation from Fn to Fm with m by n matrix A, and let S be a linear transformation from Fm to Fk with k by m matrix B. Then the product C, which is B times A, so the product of two matrices B and A, is defined as a matrix of the linear transformation, which is a composition S composed with T. And this will be Fn to Fk. And now this discussion tells us how do we compute this matrix C. So what we see is we have the following rule, that column number I of the matrix C, right? So this is going to be the vector S of T of EI, is equal to the product of a matrix B times column number I of matrix A. And in this way, we can compute all columns, right? So I goes here from 1 to n. And in this way, we fill matrix C. In fact, we have a correspondence between transformations from Fn to Fm and m by n matrices. Every transformation determines a matrix, and every matrix determines a linear transformation. So conceptually, when we think about matrix product, we should think about composition of linear transformations. But if we only want to calculate the product of two matrices, so here this can be done on the level of matrices. So this rule tells us what should we do exactly to compute the product of two matrices. So let's consider an example. So let T be a transformation from R2 to R2 with matrix. So this will be a 2 by 2 matrix, 1, 2, 3, 4. And let S be a transformation from R2 to R3 with 3 by 2 matrix, which is the following. So 1, 5, negative 2, 2, 0, 3. So let's call this matrix A and this matrix B. Then composition S composed with T. So this will be a transformation from R2. So T sends R2 to R2 and S sends R2 to R3. So this will be a composition from R2 to R3 with matrix which is the product of B times A. So let's call this C. So this product B times A is, so we have a 3 by 2 matrix, 1, 5, negative 2, 2, 0, 3, times a 2 by 2 matrix, 1, 2, 3, 4. Now, what is the first column of the result? To compute the first column of the result, we take the first column of matrix A and we multiply matrix B by this column, right? So to do this, so we take rows of the matrix B and take dot products of the row of a matrix B with the first column of A. So here we have 1 times 1 plus 2 times 3. So this is 7. And so this is the first entry in the first column of the result. So then we take the second column of matrix B and we take the dot products with the first column of A. So we get 5 times 1 plus 0 times 3. So this gives us the second entry in the first column of the product. And then we take the last row of B and multiply with the first column of A. So we have minus 2 times 1 plus 3 times 3. So this is 9 minus 2, that's 7 again. So this gives us the first column of the result. Now we do the same thing, only now with the second column, right? So the second column of the product is the product of matrix B with the second column of matrix A. So here we have 1 times 2 plus 2 times 4, that's 10. 5 times 2 plus 0 times 4, that's 10. And negative 2 times 2 plus 3 times 4, so this is 12 minus 4, that's 8. So this matrix is the product of these two matrices. If we think about this computation, we can reformulate our rule for computing the product of two matrices in a more symmetric way. So if the matrix C is the product of matrices B and A, then entry in row number I, column number j of the matrix C is the dot product of row number I of the matrix B with column number j of the matrix A. So for example, how did we calculate this entry 5? So this is this 5 is in row 2, column 1. Well, this 5 was computed as a dot product of row 2 of B with column 1 of A, right? So 5 times 1 plus 0 times 3. Let us write down what's row number I of B. So this is the following row. So we have here entries BI1, BI2, BIM. So what is column number J of the matrix A? This is A1J, A2J, up to AMJ. Now, so this tells us that if C is the product with B with A, then the entry Cij, so this is the entry of matrix C in row I, column number J. So this is the dot product of these two vectors. So this is going to be BI1 times A1J plus BI2 times A2J plus BIM times AMJ. And so then this formula can be written in a compact form using the following summation notation. So we use a sigma notation for summation. So we write sigma. So this is Greek capital letter S, which stands for sum here. And we say P runs from 1 up to M. And we write down BIP times APJ. Right? So this notation means that, so we take a sum. When P is equal to 1, we get BI1 times A1J. So this is this term. When P is equal to 2, we get BI2 times A2J, and so on. When P is equal to M, we get BIM times AMJ. So this is a compact way to write down the summation above. So this becomes a formula for computing entries of the product of two matrices. So if we have our transformations T from Fn to Fm, so with M by N matrix A, and S from Fm to Fk with K by M matrix B. So then here we could look at the following picture. So we have Fn being mapped to Fm and Fm being mapped to Fk. Then here we have T and we have S. Then if we take the composition, so this composition will be S composed with T, right? So well, T is the transformation that's applied first. And we can see that we can compose S with T only if the values of t are in the same space as the arguments of S. On the level of matrices, if we have the product C is the product of matrices B and A, then A here is an M by N matrix, and B is a K by M matrix. So we can form this product only if the second dimension of the left factor matches the first dimension of the right factor, right? So if these two numbers do not match, then we simply cannot form the product of these two matrices, and we cannot form the composition. But if they match, then the dimension of the product will be K by N. So these matching numbers will disappear, and we take just the left dimension of the left factor with the second dimension of the right factor. We can also see that we need to have matching dimensions here from this calculation, right? So here we take dot products of rows of B with columns of A. But we can form a dot product only when two vectors have the same number of components. And so this means that the length of the row of B must be the same as the length of each column of A. And this tells us that these two numbers must match. Let us look at one more example. So let S be a linear transformation from R2 to R2, which is a composition of a rotation of R2 45 degrees counterclockwise, followed by a reflection with respect to x-axis. Find the matrix of S. So the geometry of this transformation is the following. So we take some vector u, and first we rotate this vector by 45 degrees. So this is a 45-degree angle rotation. And then after this, we reflect the result. We take the mirror reflection with respect to x-axis. And then we get this vector here. And this is S of u. So this is our transformation. First, we rotate 45 degrees, and then we take the mirror image with respect to x-axis. We need to find the matrix of this transformation. So the way how we are going to do it is we are going to first find the matrix of the rotation, and then we find the matrix of the reflection. And finally, we take the product of these two matrices. So in general, we know that rotation matrix for angle alpha counterclockwise is the following matrix. It's useful to remember it. Cos alpha, sine alpha, minus sine alpha, and cos alpha. So the rotation for 45 degrees is so cosine and sine alpha for 45 degrees is 1 over square root of 2. So we get 1 over square root of 2 1 over square root of 2, minus 1 over square root of 2, and 1 over square root of 2. So next, we look at reflection in x-axis. So to construct this matrix, let's call it T, we take images of basis vectors. So this is our rule. To find the matrix of a transformation, compute images of basis vectors. So the first basis vector, 1, 0, is on the x-axis. So when we take its mirror image with respect to x-axis, this vector doesn't move because it is on the line of the mirror. So this means that the vector 1, 0 gets transformed into itself, 1, 0. So the first column of this matrix is 1, 0. So if we take the second basis vector, 0, 1, then its mirror image is going to be the opposite vector. So this vector is 0, negative 1. So this tells us that the second column of the matrix T is 0, negative 1. Now, for composition, we need to write these two matrices in the correct order. So this means that the second transformation is on the left and the first transformation is on the right. So here the first transformation is the rotation. So this means that rotation matrix is written as a right factor. And the reflection matrix is written as a left factor. And now we take the product of these two matrices. Now we apply our rule. To compute the entry in the first row, first column, we take the dot product of the first row of the left factor with the first column of the right factor. So this entry is 1 over square root of 2. So then the entry here is going to be the dot product of the first row with the second column. So this is minus 1 over square root of 2. Then the entry in the second row and first column is the dot product of the second row of the left matrix with the first column of the right matrix. So this is going to be minus 1 over square root of 2. And finally, the entry here is the dot product of the second row with the second column. And what we get is minus 1 over square root of 2. So this is what we get here is the matrix that we seek. So this is matrix of this composition. Now, let us discuss algebraic properties of matrix product. So we have the following properties. So if we consider the product of matrix A with B plus C, right? Okay, so here, so if this matrix is n by m and B is m by k, well, in order to add two matrices, these two matrices must have the same size. So this means that matrix C must also be m by k. And so these indices must match in order that we can form the product, right? So then what we'll have is, so this is equal to A times B plus A times C. So likewise, we have the property that if we multiply matrix A with the multiple of a matrix B, so here S is an element of the field, then this is the same as S times the product of A times B. So the same properties can be applied to the first factor. So if we have matrices B plus C So now these are m by k each. And we multiply it by matrix A. Now this matrix A must have size k by n, right? So now we have to have these dimensions matching. Then this is equal to b times A plus c times A. And likewise, s times A times b is equal to still s times A times b. So we also have special matrices that play the role of numbers 0 and 1. So we have a 0 matrix. So let's call this 0 m by n. So this is m by n matrix filled with 0 entries. Then this 0 matrix has the property that A plus 0 is equal to A, and A times 0 is equal to a 0 matrix, right? Of course, dimensions should match. So if this is m by n, and this must be k by m, so this 0 matrix will have possibly a different dimension. So it will be size k by n, right? And so likewise, so in the other order, so 0 times A is equal to 0, right? Well, dimensions should be appropriate here. And, well, 0 plus A is equal to A. So I leave verification of these properties for you as an exercise. And the way to prove this, so use the formula for the product, right? So we know that the entry Cij is the sum p goes from 1 to whatever appropriate index m. Well, if C is A times B, then here we're going to get A IP times B Pj, right? And so use this formula to establish equality of entries on the left and on the right. So we defined the identity transformation. So T from Fn to Fn. So this is a lazy transformation that does very little or practically nothing. So it takes any vector v and transforms it to itself. So v here is a vector from Fn. So it takes input and returns the same output. And so this is called identity transformation. So this identity transformation gives rise to identity matrix. So for a transformation from Fn to Fn, so this will be a square n by n matrix. And we're going to denote it I or Im. And so what's the matrix of identity transformation? Well, to write down the matrix of a transformation, we take images of basis vectors and place them as columns. So the first basis vector is 1, 0, 0, 0. What is its image? Its image is itself. So this means that the first column of identity matrix is 1, 0, 0, 0. So the second column is the image of the second basis vector, 0, 1, 0, 0, 0. But again, the image of this vector is itself because we are talking about identity transformation. And so the image of the last column is going to be the last basis vector, 0, 0, 0, 1. So what we see is that we construct a matrix that has ones on the diagonal and zeros elsewhere, right? So we have a matrix that has ones on the diagonal and zeros elsewhere. So this matrix plays the role of the number 1. And it has the following property, that identity times A is equal to A. Right? So where I is n by n, and A is n by m. So then we get n by m matrix. And vice versa, so B times identity. So if I is n by n and B is k by n, then the result is going to be B, which is a k by n matrix. Right? So this multiplicative property of identity matrix are the same as multiplicative properties of number 1. And we can see very well why this happens. So if we think of A as a linear transformation, then we apply transformation A, and then we apply the lazy identity transformation. So the result of this composition is the transformation A. And the same here, so we apply the lazy identity transformation. So we do nothing. So if we took input V, then after we apply the identity transformation, we still have vector V. And then we apply transformation corresponding to matrix B, and the composition is again transformation with the matrix B. So we can also see this on the computation level. So if we have a matrix 1, 2, 3, 4, and we multiply it by identity matrix, which must be 2 by 2 in this case. So then the dot products will give us, so here we get 1, here we get 2, here we get 3, and here we get 4. So what we see is that A times identity is equal to A. So one of those properties. Let us mention the following important fact. That multiplication of matrices is associative but in general not commutative. Now, what are we saying here? So what's the associative law for the product? So this is A times the product B times C is equal to A times B times C. Right? So in order for these products to be defined, so if A is m by n, then for B we must have a matching index n by k, and so then this product will have the size m by k, and C must have size k by s, right? And then on the left, right, and overall, so this product will be a matrix of size m by s. And here, so B is an n by k matrix, C is k by s. So this product is n by s, and A is m by n. So again, this whole thing is of size m by s. And not only the sizes match, but the claim here is that the left-hand side is equal to the right-hand side. So this associative law follows from associative law for compositions of functions. So we started this lecture with proving that compositions of functions are associative in the greatest generality. And so we have to remember that the product of matrices corresponds to composition of corresponding linear transformations. And because linear transformations are functions, their compositions is associative, and this gets reflected in the language of matrices into associative law for the matrix product. So the second claim here is that we should never expect commutativity of the product of matrices. So this means that in general, A times B is not equal to B times A. Now, let's see this. So suppose A is the following matrix, 1, 1, 1, 1. And B is the matrix 1, 1, minus 1, minus 1. Then what is A times B? So here we have 1, 1, 1, 1 times 1, 1, minus 1, minus 1. So this equals. So we take dot products of rows with columns. And here we see that this dot product is equal to 0. And actually, so are all other dot products. Now let's calculate the product of the same matrices in the opposite order. So we have 1, 1, minus 1, minus 1 with 1, 1, 1, 1. We take dot products of these rows with these columns. And here we see that this dot product is equal to 2. The next dot product is also 2. And then this dot product is negative 2 and negative 2 here. And we see that the results are drastically different. So this means that A times B is not equal to B times A. So we also see from this example that in matrix product we could have divisors of 0. Right? So here we multiplied two non-zero matrices and obtained a zero matrix as a result. So this non-commutativity of matrices should be remembered, and one has to be very careful with this property. Let us point out that even if the product A times B is defined, the product B times A may not be defined at all. Because here we should have matching indices. If this A is m by n, then B should be n by k, right? And if we change the order of these matrices, then B becomes n by k, and A becomes m by n. So unless k is equal to m, we cannot even interchange these two factors. Now, let us point out one special case when we don't need to worry about compatibility of matrices for their products. So here we could have square n by n matrices. So here we can add, so the sum or a product of two n by n matrices is again an n by n matrix. And for such matrices, so let A be a square matrix. For such matrices, we can define powers of a matrix. So we can define A squared is A times A, or A cubed is A times A times A, and so on. So these products are all going to be matrices of the same size. Let us prove the following theorem that tells us the relation between matrix multiplication and transposes. So let A be an m by n matrix and B be an n by k matrix, so that the product of A times B is defined, right? So we have matching indices. So then the transpose of the product A times B is equal to the product of transposes, but in the opposite order. It's B transpose times A transpose. Now, let us give the proof of this theorem. So here, first we want to introduce some notations. So we set C to be A times B. Then we are going to call A transpose as P, B transpose as Q, and the product B transpose times A transpose, which is Q times P, we're going to call it as R. What are the sizes of these matrices? So when we have a 2 by 3 matrix, its transpose becomes a 3 by 2 matrix. So this means that the size of matrix P is going to be n by m. And the size of the matrix Q, it's a transpose of B, is going to be k by n. And here in this product, so we have k by n matrix multiplied by n by m matrix. And so the result here is going to be a k by m matrix. And so what we need to prove well, this formula says that C transpose is equal to R. So this is our goal. What is the relation between the entries in the matrix A and its transpose? So when we write the transpose, we write rows as columns and vice versa. So this tells us that the entry Pij in row I, column J of matrix P, which is A transpose, is the same as entry Aj in row J, column I of matrix A. So this means that we have the equality that Pij is equal to Aj. So for entries of matrix and its transpose, we just swap the indices. So this tells us that, so if we need to prove that C transpose is equal to R, so this is equivalent, so C transpose is equal to R, is equivalent to saying that Cij is equal to Rji. Let us compute both sides. So what is Cij? Well, the matrix C is the product of A and B. So what we get is we get that Cij is the sum as goes from 1 to n. Well, n is the common index in A and B of AIS times BSJ. So this is our summation formula for the entries of the product of two matrices. What is the formula for Rji? So R is the product of Q with P. And again, we have common indices n. So this is the sum, S goes from 1 to n, of QJS times PSI. But what is this? So Q is the transpose of B. So we get the sum, S goes from 1 to n, of, so Q being the transpose of B, so QJS can be written as B, and we swap these two indices, BSJ. So this is because Q is the transpose of B, times P is the transpose of A. So PSI is the same as AIS. And what we see is that we get exactly the same expression. Well, we use commutative law in the field and we get the equality. So what we see is that RJI is the same as CIJ. And this implies that that C transpose is equal to R, right? But C transpose is A times B all transpose, and R is the product of Q times P, which is B transpose times A transpose. And now we prove this theorem. Let's consider one more example on composition of linear transformations. So consider a composition of a rotation of R2 by angle alpha counterclockwise, followed by another rotation by angle beta, also counterclockwise. So here we have a composition of two rotations. So we have rotation in angle alpha followed by rotation in angle beta. Now, if we take a composition of these two rotations, clearly the result is going to be again a rotation in the angle which is the sum of alpha plus beta. Now, let us translate this equality into the language of matrices. So we know that R alpha is, so the rotation matrix has the following structure. It's cos alpha, sine alpha, minus sine alpha, and cos alpha. So now let us compute the matrix in the right-hand side. So matrix in right-hand side. So here we get the product of two rotation matrices. So we have cos beta, sine beta, minus sine beta, cos beta times cos alpha, sine alpha, minus sine alpha, cos alpha. To compute this product, we take dot products of rows of the first matrix with columns of the second matrix. So the entries of this 2 by 2 resulting matrix will be complicated, but still this is a 2 by 2 matrix. So here we are going to get cos alpha times cos beta minus sine alpha times sine beta. So this is the first entry. So the second entry, we take the dot product of the second row with the first column. So we get cos alpha times sine beta plus sine alpha times cos beta. Now the second column. We get minus sine alpha times cos beta minus sine beta times cos alpha. And the last entry, we take the dot product of the second row with the second column. So we get minus sine alpha times sine beta plus cos alpha times cos beta. So here we get this complicated 2 by 2 matrix. Let us write down the matrix in the left-hand side. So in the left-hand side, we have a rotation matrix in angle alpha plus beta. So this rotation matrix has the same pattern, only a different angle. So we get cos of alpha plus beta, sine of alpha plus beta, and here we have minus sine of alpha plus beta, and cos of alpha plus beta. Now, comparing the matrices in the left-hand side and the right-hand side, we obtain the well-known trig identities. We get that cos of alpha plus beta is equal to cos alpha times cos beta minus sine alpha times sine beta, and so this entry we get sine of alpha plus beta is equal to this expression here. So we get sine alpha times cos beta plus cos alpha times sine beta. So this becomes the cleanest and simplest proof of these trig identities. And so this shows the power of linear algebra, so that this matrix multiplication allows us to derive trigonometric identities in a very easy and conceptually clear way.